from is building a robot called the HAVOC. And before I turn that over to them, I want to thank our panel for showing up today and for being here to evaluate the students. We have Dr. Bordignon, Dr. Bruder, Dr. Davis, Dr. Skipper, and our guest panelists, Bryce Mills and Bryce Chanis. So thank you again for coming, and with that, I'm going to turn it over to the students.
Hi, my name is Crystal Doggio. This is Sandy Freeman, Jared Dellinger, Sean Jones, and Adam Catfias, and we are HAVOC. Today we are going to talk about the project description and the purpose, along with the progress we've made this semester. We're going to go into detail about our CAD design of the hand and the forearm. We're going to go over the finite element analysis test on the CAD model. We'll talk about the forward and inverse kinematics along with the equation of motion simulation. We'll cover the projected budget of our project, the schedule for next semester, the requirements and specifications that we have met, and answer any questions you might have at the very end. So the purpose of this project is to construct a hyperdexterous animatronic vision-operated contraption. This robotic hand will move based off of an operator's hand using a glove with LED lights on it. The motion capture system will grab the LED light location, send that data to the robotic hand. The robotic hand will then be able to perform human hand tasks in real time. The robotic hand is made up of 3 subsystems: the physical robotic hand, the software, and the motion capture. The physical robotic hand will be a robotic hand that will have the sizing dimensions of one of our team members. It will also have a forearm that will house the electrical components. Now the software will contain the inverse kinematics and the control law that is necessary to translate the motion capture data to actuation commands for the robotic hand. Now in the motion capture system, we will have a motion tracking system that will capture the orientation and position of the LED lights and send that data to the software subsystem. Now, what makes our project unique is the very fact that it is compact, versatile, and it is capable of overcoming the the dexterous limitations that a lot of specialized robotic end effectors cannot. In addition, this project can be used in manufacturing assembly lines, and it can be used as a prosthetic arm. Now the progress that we've made this semester we have finalized the CAD models, we have programmed the dynamic simulation, and we have received data from the motion tracking system. I will now hand it off to Sandy Freeman, who will talk about the CADs.
So here's an overall picture of our CAD design. This is the entire assembly. There's 2 main components. There's the robotic hand on the left there, and then on the right here, there's the forearm. They're connected by a wrist connection. That's a wrist joint in there. And I'm going to be going into detail on how this robotic hand meets our specifications. The robotic hand specifications, or the specifications that were specific to this design, was that it needed to model the hand of a team member. We had to use dimensions from a team member to actually build it in order to make sure the size was similar. Additionally, we chose that it needed to be actuated by wires in order to properly imitate the motion of a human hand. Also, in order to achieve the dexterity that we needed for this project, we determined that we needed a minimum 18 degrees of freedom on the hand. So as you can see here, we split up the hand into, in total, if you count those up, that's actually 22 degrees of freedom. There's one more degree of freedom on the hand, which is actually the twist rotation of your wrist. That was excluded from our model. Additionally, to reduce our degrees of freedom from 22 down to 18, the joint between the fingertip and the next joint we chose to fix that. So that's going to be a fixed angle, and that simplifies both our dynamics, but it also makes it so that we have more space available inside the forearm because we don't have to add actuators for that. Additionally, we chose to use some fishing line, as shown here, to act as the wires or the tendons for the hand. AxFab actually has several choices we can choose from, up to, I think, 80 pounds fishing line. And so we're looking towards using that to act as our tendons. And then the dimensions themselves were actually taken from my right hand. So we measured my entire right hand, each and every joint, and that's how we were able to get our initial measurements for the cat. So the hand itself has several components, and I'm going to go through all of them. Starting with the standard finger, we have all 4 fingers on the top of the hand are actually the same. The reason for this was to simplify manufacturing, and also it actually gives a little more dexterity. There's also the thumb, which is a different design from the other ones, and the reason why that is because the structure of the thumb is unique, and so we didn't want to copy it exactly. The palm itself, as shown here, contains basically the housing for all our tendons, so we will be able to feed all our tendons through there. I'll go into a little more detail on that soon. There's the knuckle joints, which connect the palm and the fingers together, and there's the wrist, which connects the palm to the forearm. So to go into a little more detail on the standard fingers, they consist of 4 main parts. There's your distal phalanx, which is the phalanx with your fingertip on it. There's the middle phalanx, and then there's the proximal phalanx, which is closest to your knuckle. And then the knuckle itself is down at the bottom. We chose to use a standard joint design as shown here. It's a double lap joint with a smooth bolt going through it, and the reason for having a smooth bolt is so that we can reduce friction, so it's very easy to actuate the fingers. Here is a picture of the proximal phalanx on the standard finger. It consists of 2 main components. There's the phalanx itself, and then there's the phalanx cover, which cover up the tendons. As you can see, we have multiple passageways for the tendons to pass through. We can send them in through the bottom here and send them actually through the entire finger, through the entire phalanx up to the next one if we want to. That way we can actuate multiple joints within the finger. Additionally, the bolts up here we will use as attachment points for the tendons. The way we'll do that is we'll simply tie our fishing line around those as we bolt them in. And then there's threaded holes on this side on this cover on the back to help hold it all together. The middle phalanx is very similar. It's basically just a smaller version. There's only 1 bolt in there. But again, the passageways are the same. There's 2 phalanx covers that sit over it. Backbone is threaded the same as the proximal phalanx. And then the distal phalanx is slightly different because of the size. We had to put the bolt on the back instead of the front. And into a threaded hole, and then we created a notch here, right at the bottom of the fingertip, so that we can tie the tendons to this little notch. So with those designs, we can configure the tendons in a variety of ways, and that gives us a lot of flexibility going into details this time. The thumb itself is, again, very similar to the standard finger design. The biggest difference is that the proximal phalanx and the distal phalanx are both bigger, and then the middle phalanx is actually smaller. And the reason for this, again, is because the structure of your thumb is quite different from your other fingers. The knuckle joint itself consists of three main components. There's the knuckle joint, then there's the bearing that is press fit into the palm, and and the knuckle joint is attached to that using a hex nut. And the reason for the bearing is, again, to reduce friction, so that we have low torque requirements for actuating fingers. The palm, as seen here, has many features to it. Beginning with there's a big slot here for the thumb to sit in. Additionally, there's multiple passageways. Starting in the bottom, you can feed your tendons through the bottom up onto the inside of the palm, and then out through the holes at the top here into your fingers. Additionally, the thumb, because it's oriented differently, has a small passageway cut into the bottom, into this thick portion of the palm, and that's, again, so we can feed tendons to it. And then there's additionally some bolts at the bottom of the wrist that are used to attach the bottom of the palm that are used to attach the palm to the wrist, and then also can be used as connection points for tendons. Here's the wrist itself, mainly three different parts. We have the top of the wrist, which connects to the palm. It has two holes in it, a tendon passageway through the center, and then there's also a hole right here so that we can fit the nut for the thumb on there. There's the middle section, or the wrist connector, which connects the two parts of the wrist. This was designed so that we could have a loose fit on both the top of the wrist and the bottom of the wrist, so we can have easy, simple actuation. There's some threaded shafts that can be screwed into this block in the center, and that's how we will connect everything together. And then there's the bottom of the wrist, which connects directly to the forearm. We had some additional specifications just to make sure that we met kind of kept our size requirements and such. One of which was we measured from the base of the palm to the top of the middle finger, and we measured that to be about 19.5 centimeters. So we made a specification saying, okay, we want that distance to be 19.5 centimeters, so that we don't make a hand that's very big or very small. As you can see here in our CAD, when we measure that distance, it comes out to about 19.6 centimeters, which is good enough. Also, the robotic hand has to be big enough to hold a Rubik's Cube, or a 5.6 centimeter cubed square. As you can see here in our CAD model, we just threw one together, and it fits very snugly on our hand. And finally, the mass, the weight of the system. Our requirement states that it needs to be lightweight, and therefore we decided that it needs to be at least less than 15 pounds. Now, based on our current CAD model, with all the materials applied, the mass comes out to 1.96 pounds, so not very heavy. So we expect to meet that requirement fairly easily. And just to clarify, I realize it does say mass, which might suggest that it's in pounds mass. It is actually in pounds force. Just SolidWorks outputs it that way. And now I'll hand it off to Jared Dellinger to talk about the forearm structure and the FEA.
Moving into the forearm, we had a requirement that the forearm needed to match our very own Sandy's forearm. So the length minus the Sawyer mount and the wrist needed to be at most 23 centimeters. As you can see from the schematic here, it meets that requirement if you count this platform right here as being on the inside of this mount piece here. The servos are arranged on each of the 4 sides, and this allows us to hold the 18 servos so that we may have 1 per degree of freedom, and it will be printed out of a 3D resin that will be discussed in the finite element analysis. The actual structures inside of the forearm are the wrist connection here. It will be bolted onto the front end of the structure here. That will also connect to the wire leads. As you can see, the wires will be fed around here and into the servos and then back out. And that will allow us to rotate the servos around and get a forward and reverse revolution. The microcontroller that will control these servos will be housed in this open section in the cavity between the wrist and the internal structure. And there is a possible addition of a transparent casing not shown here that will cover the system to protect it from any external forces that might damage the internal components. For the forces that will be applied, we use ANSYS to apply a force of 25 pounds to the end of the frame of the forearm to anticipate the loading of the 10-pound minimum with factor of safety of 2 onto the edge of our hand. The ANSYS simulation shows that the maximum forces will be felt here, and maximum stress and strain will be felt here. But according to our data sheets that we reference, they do not exceed the maximum ultimate tensile strength and strain. The ultimate tensile strength is 55 megapascals, and this is 44 megapascals. And on the strain, the maximum elongation of the material was 24%, and it does not exceed 4.04. The fingers were tested 5 pounds each to distribute the factor of safety 20-pound load across each of the individual 4 fingers. And that was applied to the center of the finger. And that showed that the maximum tensile strength and strain were not exceeded by that force application. And lastly, the stresses were plotted into the wrist if the wrists were in a downward position with all the force maximized and the positive y direction. Again, this material, however, is an aluminum alloy that the ANSYS software had data for, and the aluminum could hold both the strain and stress and not exceed its minimum requirements. The deformation in this part here is exaggerated to reveal the maximum stress points, such as this one on the underside of the platform of the wrist. Moving on, we will go to Sean Jones with the board and inverse kinematics.
Thank you, Jared.
All right. So why kinematics? Kinematics are used to map the configuration of a robotic system using joint space parameters and within a specified workspace. Board kinematics specifically are the calculations used to take the joint space parameters and convert them into task space end effectors. Whereas inverse kinematics go in the opposite direction, where you have a task space or end effector and convert that into joint space parameters. What we have right here is a typical problem that you would see for forward kinematics within robotics, where we have two frames, frames A and frame B, and we have a point in 3D space, point I. Now, what we want to do is find the positional vector of point I with respect to frame B. However, we only have the vector from going from frame B to frame A, and the vector from frame A to point I. Now, you can't just add these two vectors together to get this vector right here. What needs to happen is that you need to transform the vector going from A to point I to be with respect to frame B. To do this, you would multiply the vector by a transformation matrix that accounts for the orientation of frame B with respect to frame A. And another thing to note is transformation matrices can be multiplied together to create a single transformation matrix that will orient from the initial frame all the way to an end effector frame. So three common transformation matrices that you'll see are rot X, which indicates a rotation around an x-axis, rot Y, which will indicate a rotation around the y-axis, and rot Z, which will indicate a rotation around the z-axis. And over here, for the preceding equations, I have this is a definition for simplification's sake of where you would normally see II or little I, or the initial frame with respect, or going to the target frame. I simply just say R to the target frame. So some preface for the problem right here. Given the allocation and amount of LEDs that we possess, we can break down what would normally be a 6-degree of freedom problem going from the forearm to the for each fingertip down into multiple smaller problems. As a result, we can simply just look at for starting with the wrist, we can just look at the rotation joint, or the point of rotation along the wrist, as the beginning of this question. What you will see right here is R0. R0 in this instant indicates any calculations that were taken up to that point. For the purpose of the equation right here, or the problem right here, you can simply consider it to be 0, as the initial frame for this problem is right here. But that is just to clarify that there are calculations taking place. Now, specifically for the wrist, the forward kinematics include first a rotation around the y-axis, which would do a tilt from left to right. And then we would have a rotation around the x-axis, which would do a bend of forward and back. Now, for the standard fingers. As all the 4 fingers on the top of your palm use the same model of finger, you can use the same equations for the kinematics, just at a different offset for R0. For the fingers, what happens first is a rotation around the x-axis, which would cause a tilt from left to right. Following that, on the proximal phalanx, you get a rotation around the y-axis for the bending forward and back. Then for the middle phalanx will be, again, a rotation around the x and y-axis. However, around the y-axis, there'll be an additional theta to account for the angle right here. And then following that, the distal phalanx will again do a rotation around the x-axis and do an additional rotation around the y-axis with a theta of 3. For the thumb, as the shape of the thumb and the way it actuates is very similar to the other fingers, the kinematics involved with it are very similar as well. However, the only difference is that it actuates around different axes. For the thumb, when it does a tilt, it will do it around the z-axis. And when it does a bend, it will do it around the x-axis. Now, for the inverse kinematics. The inverse kinematics, as they are taking task-based positions and turning them into angles, we'll be using trigonometry to grab the angles theta and theta 1 and theta 2. Right here are my equations for grabbing both of those. For the fingers, due to the fact that we have the angle between the distal and middle phalanx being fixed, we can simplify the problem of what would normally be a 3-degree of freedom problem down to a 2-degree of freedom problem. And this reduces the amount of calculations we would need to make for those thetas. Right here are the equations I would be using to, or I am using to calculate these theta 1 and theta 2 right here, as well as theta 4. Again, the thumb is very similar to the finger, so it will be using the same equations. However, it will be doing around different axes. All right, I'll now be handing it back to Crystal for her to talk about the equations of motions and the simulations.
So the equation of motion is a mathematical calculation that demonstrates the dynamic motion of the robotic hand when a force is applied on it. In order to get the equation of motion, we first have to take the kinetic energy, which is originally mass, 1/2 mass times velocity squared, and expand it to the translational, coupling, and rotational kinetic energy. We also take the potential energy, which consists of the mass, a gravity vector, the position vector, the transformation matrix, and the center of mass vector. With this, we can separate the equation of motion into 3 parts, H, D, and G. H is the system of mass matrix. We get it by taking the partial of the kinetic energy with respect to gamma dot. Gamma dot is the derivative of the joint parameters. In order to find D, the Coriolis and centrifugal terms, we take another step of the partial of kinetic energy with respect to gamma dot. Now to get the gravity vector, we take the partial of the potential energy with respect to just gamma. Now combining all of these together, we can construct the equation of motion, which can then be used to create a control system. Here is the simulation of the equation of motion with 0 forces acting on it. As you can see, the fingers are moving the way they are supposed to, and the wrist is not moving as much only because it has a great coefficient of friction. I will now pass it to Adam to talk about the motion capture.
Thank you, Crystal. So in order to capture the user's position and orientation data of their hand, we're using the face-based X2E motion capture system, which has a high resolution of 130 megapixels and a high refresh rate of 960 frames per second. The system uses a camera array to sense LEDs, which each have their own unique ID signature that is dependent on the operational frequency that is determined by the face-based system. The user, depending on from the orientation that we have of the placements of the LEDs on the glove, we can get the user's orientation data through our own kinematic calculations. With the face-based system, it records the LED marker's position in XYZ data and its ID number. We have created a MATLAB script function that will read the latest updated values that is output to a file, that the face-based outputs to a file, and we read those into an array. We also check to see that all LEDs have received a position update, and if there is not, then we send the previous array to ensure that there's no failures in our kinematic equations. Here's an example of our motion captures system working. You saw there we have the glove moving, the LEDs that the face-based is capturing. On the right
right here, we have the face-based motion capture program that is showing the LED markers. On the left is our MATLAB script grabbing the data position values from the face base and translating them to a skeleton model of the hand. Moving on to our electronic system, we have chosen to use an Arduino Mega 2560 R3 because of its high number of pins and because the servo library allows us to operate our large number of servos without problems. In order to connect all of our electrical components to the Arduino, we are creating a shield that will attach directly to the Arduino. We have 18 3-pin connections for all of our servos. Each one will have a direct connection to an I/O port on the Arduino to send signal for the servo angle. We also have a power connection to an external power supply that will go outside of the arm to an external power supply, and a kill switch will be implemented in that line so as to have access to it outside of the arm. We also have 5 voltage dividers to convert the force-sensitive resistor values that we'll be using to detect force on the tips of our fingers, and those will be connected to the ADC ports on the Arduino Mega. Here's a preview of our shield. You can see the placement of the 18 3-pin connections for the servos here and here. We also have 5 2-pin connections for the force-sensitive resistors and the placement for the resistors for the voltage dividers. For our force-sensitive resistors that we'll be using to detect force on the tips of the fingers, we have chosen the SparkFun 1/2-inch FSR. It has a sensing range of 100 grams to 10 kilograms, which will allow us to sense our specification of 0.5 to 2.5 pounds of force. It also has a maximum resistance of 1 mega ohm when there's no force applied, which will work perfectly for our 10 kilo ohm resistors in our voltage dividers. For the servos, we have chosen to use an ES9256 servo. We've chosen this one because it is small, and for its size, it has a high torque and a high speed compared to other servos. We need to find the total force that each finger needs to apply from our specification of a 10-pound weight that the hand must hold. And this comes out to about 11 newtons per finger. The servo torque we can estimate to be about half of the stall torque, which is about 1.7 kilograms of force per centimeter. We've also made calculations to determine that we need about 3.5 centimeters of travel to actuate the fingers. The tendons that we'll be using will wrap around the servos, the servo horns, and upon rotating, it will retract and it will actuate the tendons. So we need about 3.5 centimeters of travel, and our specification was to curl the finger in about 1 second. So we divide that by 1 second, and we find that we need a speed of about 0.23 seconds per 60 degrees. Which you can see on the servo, we have about 0.05 seconds per 60 degrees. So this easily meets our specification. For our servo actuation, we are using a robot operating system to communicate with our Arduino on our robot hand. Programs in robotic operating system, or otherwise known as ROS, act as nodes, and these nodes can connect to communication lines called topics. Any node that is subscribed to a topic will receive all the data that is transmitted to that topic, and any node that is, for our system, we are using a angle publisher running on Linux that will publish the angles in an array to the servo topic. This will then be read by another node on the serial port, which will allow the Arduino to read this array of servo angles. Here we have a demonstration of our electrical system working. We're running 7 servos. We can run them each individually as well as all simultaneously. I'll hand it back to Crystal Baggio for the estimated cost and gain share.
The overall cost of this project is going to be $615. A lot of this will be coming from the servos, the 18 servos that we will purchase, but they are compatible for our control system. Here is the project schedule for next semester. As you can see right here, we have a feasible time that if we need to do fabrication or test more things, we will have enough time to do so. So this semester, we've met a numerous amount of requirements and specifications. The ones with question marks means that we have not met them yet, only because we need to build the robot hand in order to know if we have met these requirements and specifications. Here's a continuation of the requirements and specifications that we have met. And lastly, the reason why we have a question mark here is because we need the entire system to be built in order to know if we have met that specification. We'll now open up to any questions you may have.
There was a comment made that the tendons would attach to the horns of the servo, but there wasn't much detail in how that was going to happen. Can you speak a little bit more to how you intend to attach the tendons to the servos and how many tendons you intend to have per servo?
So that would be a great question for Sandy, who is doing the
Yeah.
kind of design.
So the way we intend to attach the tendons to the servo is we'll likely use some sort of serrated surface on the inside of we have like a ring, or sorry, a disc that we'll be using to rope it to actuate those. We can also attach it using glue or something like that if necessary as a prototype method, or you wrap it around the top and wrap it around multiple times. That hasn't been fully fleshed out yet.
That's a critical aspect of the design, and I would say that should be included in a design review because that's something you want feedback on.
Okay.
The second part of that question was, how many tendons per servo?
So there's going to be 1 tendon per servo, but in order to actuate, sorry, I guess it's technically 2 tendons per servo because we're trying to actuate the link in both directions. So it basically ties to one side of your finger, goes all the way down to the servo, wraps around, comes all the way back, and then attaches to the other side. So that way we can get bidirectional motion.
Again, that 2 tendon aspect would have been an important thing to have in the design presentation as well. You mentioned that you're going to have the force feedback resistors, but you didn't say where in your mechanical system those are located. In the mechanical discussion, there was no placement of the force resistors. Can you go back to the mechanical and say where exactly will those reside in the hand assembly?
Yeah, so right here, there's a flat surface on the distal phalanx, and we'll just attach it to that.
So it's only going to be a flat surface of the fingertip, not the fingertip as an entirety.
Yes, just the flat surface.
Okay.
Related to the tendons, go to page 20 for me. So you're feeding the tendons through those wire leads and separators you done any looking into wear and tear on those tendons? As they slide through there, or how to reduce wear and tear on that?
We have filleted the edges and rounded them down, and we have thought about using some sort of other insert into those tubes to reduce the friction that the tendons would experience as they would rub against those surfaces.
And then on page 10, I was a little confused. You've got the tendon passageway there running down the middle, but then you're driving 2 screws right through that. How's the tendon gonna
So there's actually space on either side of the screw for
Okay.
tendons to
Okay.
go around. That's why it's a slot shape, yeah.
Okay, in one spot you mentioned an Arduino Uno, I think that was under budgeting, but then you call it an Arduino Mega. Which one are you using?
So they,
A Mega, and do you know which processors on there? Just out of curiosity. Dr. Davis tells me it's the 2560. I was curious because we used the 20.
Yeah.
And then I noticed on your torque, you said you cut stall torque in half. And if I'm reading that right, does it say 3 for the stall torque over there, 3 kilograms per centimeter?
3 kilograms at 6 volts. And it's,
At 6 volts, but then you use 3.5 over on the left side.
yeah, 3.5 is for the 7.4
Okay, I
volts.
couldn't see that. Okay, I couldn't read that properly. And why is it half? Why'd you choose half?
That's a estimation. It's for,
Yeah, so that was, we had to come up with a sort of general number for that, and that's an estimation.
So what occurs at half?
What occurs at half?
Pick on the 2 that have me in mechatronics right now. What occurs at half?
max power.
Max power. Now, do you usually operate max power?
No, you work just below that.
A little less than that. So I would probably just maybe lower that a tad. And then one last question I had is, you mentioned using this as a prosthetic. I'm a little confused because if I need a hand to control my prosthetic hand, doesn't that sort of defeat purpose?
So the idea is that with this hand, really the idea behind motion tracking glove is that you can develop the actual motor commands for the robotic hand. And you can do it easily because you just translate, human motion directly to the hand. Otherwise, you'd have to actually go in and program how does the hand move, and it would basically become you learning how to do animation, right, and make motions look real.
Okay, so then what changes would you make if you were going to, someone lost their hand, you hook that on there, what changes would you make so they could actually control it? I guess that's what my question is.
We haven't considered that.
First, let me say, it's a good piece of work on a very ambitious project. Can we come a little bit, slide 10? The tendons, we have pointed out these tendon covers. It's not clear to me why you need covers over that.
So the reason why we have covers over that is because we don't want something to, when it's grabbing an object, we don't want them to collide with the tendons, because then what's going to happen? Things get tangled, stuff like that. So the idea of the covers is to prevent that from happening.
And it seemed a little awkward when you were describing how you were going to tie tendons to the bolts while you were trying to install them. That was going to be any fun.
Well, okay. I mean, basically the way I see it is you stick the tendon through the first, or you stick the bolt through the first cover, you tie the tendon on, you stick the bolt through the rest of the phalanx, you tie the tendon on the other end, and it's ready.
And then you can tie it up, perhaps you tie it in a spot where it's not going to come down and it's very thin. Let me know how it goes.
Yeah.
And then, as the tendons are coming through the wrist, are they guided at all through there, or they all just come through as a bundle through the? No, or it comes through that hole there, the tendon passageway, they all just come through as a bundle?
Yeah, so, at the moment, it's coming through all as a big bundle. I think ultimately what we'll want to do is have little, maybe like Teflon pipes or something, for each little tendon, which will, that way they don't interfere.
I think it's important that you're been fishing with me.
Yeah.
And then on the structural analysis, first thing, what is the source for your material properties for the plastic?
We found a data sheet for the tough resin 3D printed material, and that's in.
And it's as printed condition or?
It has both. So when you print in resin, you have when you pull it right out of the printer, it's actually soft. So it gives us information on that, and it also gives us, after we curate it fully, what the numbers are.
The numbers we use were the post-it.
Yeah. Then, I know your stresses are pretty low. Is there any reason you can't put a gusset on the sides there to have all that stress?
We were going to, once we had enough, once we finished figuring out how tall the internal structure will be.
Internal structure?
Yeah, the microcontroller will have the shield on top of it, and then we still need to figure out how tall the wires connecting out of that will be, and then we will be adding supports on top of that. We also needed to figure out whether or not we were going to use more elastic or still use the 3D printed resin.
And then I think my last question had to do with the video, using the hand and go to the computer. Can I get a copy of that?
Yeah, sure.
That was really good. Then the torque calculations, did they include an account for friction?
No, those did not include for friction.
Again, it is an estimation, that's right.
There's an estimate in there, or there's no friction?
I mean, the analysis is an estimated amount of torque that we'll need to actually fingers.
And then finally, on your cost estimate, you have tax included in there?
No.
Get you, and then finally on your schedule, very good that you have a schedule margin. Members of the team in the room, you don't mention that you have that. That's all I have.
So, when I think of muscles, I think of them as torque generators because they cause rotational motion. In your analysis, did you, when you said, oh, I need to hold so many pounds of something, did you go through and figure out what the torque requirements are at the different joints in order to hold the thing?
We did that initially to kind of get some rough numbers, but it was difficult seeing as we didn't have the geometry for our system until quite recently when we finished with that. So it was difficult for us to actually get real numbers on that. We intend to do that for detailed semester.
Okay. And then, so the tendons are having to apply those torques. So what is the stress and strain on the fishing wire? I don't think you'll exceed a breaking limit, but you might have elasticity issues if it's too much. So have you looked into that yet, or is that next semester?
Yeah, well, actually, I've talked to some people about that, and they've said, that particularly some machinists in AXPAT, they said they don't think that'll be an issue with their experience with fishing line, especially with like the higher pound versions. So.
I would believe that, but as an engineer, I like to see numbers, and I like to see this is what we expect, and we're well within our margins. So I expect you probably will be well within your margins, but do the
That will
analysis.
definitely come with the testing phase, so once we produce a figure and we connect the wires, we will be testing, in real life, how is this going to react to the strains and stresses. And so then we'll have a specific number to use.
You mentioned that the distal joint, you're gonna fix that angle. I'm wondering, what angle did you choose and why did you choose it, or have you not chosen it yet?
That has not been chosen yet. That'll be ultimately determined through testing.
On slide 19, you mentioned the Sawyer mount attachment. I don't think you mentioned what Sawyer is. So I know because I hang out in the robotics lab occasionally, but for the general audience, maybe you could give us a little background on that.
For everyone else, the Sawyer robot is a 6th degree of freedom. Degree of freedom arm that currently sits in the Space Robotics Lab, and it was a potential answer to the question of how to get that last rotation about the axis for the wrist.
That's all I have.
You want to organize this? Sure. So how much time do we have left, just to make sure we're ready? So, first of all, nice job, folks. Canada say the presentation, the slides look very good. There's a company by the name of Barrett. Have you run into them in any of your research? Never heard of them? You might want to take a look. They make a reference hand design. They've been doing this for quite a while. You'd be able to get an internship or a job with them after this if you do a very good job. On that vein, did you actually look at some of the commercially available designs that you thought you might be competing, quote unquote, against?
Yes, so we looked into Shadow Robot. It is also a hyperdexterous robotic hand, but it is autonomous. It does not use a glove with any LEDs. It has, I believe, 20 to 22 degrees of freedom, but it also has 4 sensor resistors. But I believe that we have a step up because we have the glove with LEDs.
So one of the things to mention about that hand in particular is that it operates using artificial muscles that use basically air pressure. So to actually use that hand, you have to have an air pressure tank available to do that, whereas our intention is just to do it through electronics.
So you have looked at another one. Anybody else using these kind of loops, tendon designs? Because I'll be blunt and say you've heard from everybody so far, and I'm going to add my name to that list. You're going to run into challenges with these kinds of excellent loop tendon designs, because I guarantee you, throughout the articulation of the fingers, the loop length is going to change and bad things are going to happen.
Okay.
Do I correctly understand what you have is one single loop, correct? And it's predicated on the assumption that the loop length stays constant throughout motion. I guarantee you that won't happen. So you're going to run into some challenges there and have to rethink spring loading it or something along those lines. Just a heads up, this will happen.
Okay.
Can you take me to the kinematic section? I think slide 29 or a little just before that. So the lowercase r here on the diagram, what are those symbols representing?
Oh.
Positions, orientation?
So these symbols right here,
On the diagram, to the right there.
here, mean as in like the B, B, and the A?
Yes, R. What is R?
So R is simply just the variable to indicate the vector. That's going from that frame to, at least in this case, it's going from that frame to this frame. The left superscript indicates the origin point of the vector, or the starting point. The right subscript indicates the end point of that vector, as it's going from B to A. And the left subscript indicates the frame with which it is with respect to.
So that's a positional vector denoting the
Yes.
origin of B to A coordinates.
Yes.
Okay, to the next slide, please. So now, when I look at that same symbol R on the top right, what is R?
R, like with the previous slide, it's again a positional vector.
And the one on the right, the big R?
It is just a shorthand notation to represent that going from the initial frame of reference to the endpoint frame that we were
So
referring
it's
to.
still a positional vector?
Yes, still a positional vector.
Take me to the next slide. So all through this, R, uppercase R, lowercase r are positional vectors, coordinates in different manners, correct?
Can you repeat that?
So R is still a three-dimensional positional vector?
Yes.
A little confusing, I guess, the notation, because it's most commonly
So for the rotation matrix, that's what the, if you go back 2 slides, that's what's the, this right here. This is the rotational matrix itself. R's indicate a XYZ vector.
So T is not a homogeneous matrix, T is now just a rotational matrix.
No, T is a homogeneous.
Oh, no.
Not in your notation here, it's a rotational.
Yes. Yes, it is a rotational matrix.
Just a minute, is there, go for it, 2 more. So, 1 more. So when we start doing the forward kinematics and inverse kinematics analysis, there's some standard approaches that people would often use to represent robotic linkages, especially closed chain linkages, things like Denevit, Hardenberg. Dr. Isenberg, you take what, are you familiar with any of that?
Yes.
Yes, we are familiar with that.
Okay. It just makes it easier for some of us that have seen these kinds of patterns.
Consider that.
Go back on the looping tendon. How many degrees of rotations are required for the circles? More than
Oh, how much?
Total rotation.
how much- Well, okay, so that depends on the horn itself. That depends on the horn. So according to our calculations, again, based on our rough estimate for how much torque we need, that if we rotate 180 degrees, we'll be able to actuate, if we have servo horns of the correct size, which I think was, what did you say was 3 point?
It was a 2 centimeter diameter.
Yeah, sorry, 2 centimeter diameter, that's right. Then with 180 degrees, we can fully actuate the finger.
Okay, so you can't permanently attach the tendon to the horn.
Yeah.
So that hang-on friction for that.
Yeah.
There wasn't a lot of notation for factor of safety on any of the figures, particularly during the stress analysis. It was kind of just verbally mentioned, like, oh, we checked the data sheet. Sorry, the data sheet said this, and therefore we can agree to be okay. I would really like to see on all of the structure analysis side some sort of like factor of safety on what you thought the stress was going to be, or the whatever value that you're measuring against, versus that giving like a little warm and fuzzy feeling that you're not going to be breaking some of these
Yeah, so
plastic parts.
one of the things that I don't think was quite mentioned in that section is our specification says that we have to be able to hold 10 pounds. And for a lot of these tests, we use the factor of safety 2 basically, and double that so that we can make sure that that would break our system.
Okay. That would have been really good
Yeah,
to
so we should have mentioned
present on there. I was also kind of left in the dark through most of this on your material choices for a lot of things. It was only briefly mentioned, we want to use resin, or maybe we want to
cut
use
that slide out,
aluminum.
I'm sorry. Yeah, so a majority of it will be built out of resin, and the reason for that is because we have some very complex geometries. It's going to be easier to print them with resin. Also, tough resin is actually quite strong, and also there's durable resin, which is useful as well. It's similar strength, but actually low friction. So I was going to do some more investigating on that. So those are some options, and then other than that, we're going to use aluminum just to strengthen certain parts.
Right. And I'm really worried about the manufacturability of a lot of the pieces, the tolerances involved. You're doing some Prescott bearing pieces. I don't know if there's a lot of history that your group is familiar with the tolerancing that you have to do to make sure those pieces are able
so
to fit in.
one of the good things about resin printing, or the resin printers that we have, is their tolerances are 0.05 millimeters plus or minus, which is about 0.02 of an inch, which should be plenty enough for us to get the press fit that we want.
Okay. Can we move to slide 14? This is talking about the knuckle joint. You have a bearing in that system, but you have a large plate on that knuckle joint itself, the aluminum knuckle joint, and the hex nut actually appears to be larger in size in the assembly view. It seems like as you would tighten that piece, you'd actually be sandwiching against your wrist mount. I forget what material the palm is made out of. But that bearing wouldn't really, how are you monitoring, I guess, the torque in a lot of these joints to prevent something like just sandwiching between between pieces? You have a great
Yeah,
grade
so
in there, but it
well,
doesn't
one of
seem
the things
to be
that's actually quite difficult to see is there is a bit of an edge on the inside of the knuckle here, which actually displaces it slightly. So
Okay.
we aren't gonna cause jamming with the bearing that way.
Okay, and how about, is there a similar feature on the hex nut?
No, as of yet, I haven't thought about that, so.
Okay.
I think potentially I think actually though is, yeah, actually, what we were thinking of doing is we just put a washer behind it. A small space service as well.
Okay, yeah, and it needs to be smaller than the nut
Yes,
that
yeah.
was there. Slide 9, I have a similar, with this double lap feature, as you're tightening that, you're changing a lot of how much friction is involved in that joint. Is the smooth shaft bolt a common piece that you're designing around, like a McMaster car item
Yes.
part number that you're
Well,
designing
that's
around
correct.
to? And is that basically the only constraining factor for, how do you know not to tighten that nut too much before you're adding much more friction in that double lap joint? Does that concern make sense?
Yeah, that does make sense. I think the solution I had for that was basically just to make the tolerances right, so that it would be far enough away that it would be an issue.
Yeah, if I had $1 for every engineer that designed a part for me that said he designed the tolerances right the first time, or the second time, I got through the manufacturing process and made sure that the manufacturing team made it to those tolerances, it would be a lot. So I'm very concerned about the manufacturing and what kind of assumptions you were making as far as the friction redesign goes in assembly.
Thank you.
Okay, so I do want to point something out. So slide 21. So for your stress analysis, you mentioned the factor safety. So you calculated your margin to ultimate. What's your margin to yield?
The specific data sheet we had for the doctor did not have the specific yield.
Okay, that's going to be pretty important because dealing with plastic. So, the stresses might be low enough that it's not an issue, but, and I don't know how often you're going to be going to max load or whatnot, but you definitely want to know how much margin you have to yield. Because that'll probably do, like if you use this thing a couple times and you're constantly going past the yield strength, it'll only last a couple uses. So you want to know that.
We're also thinking of the possibility of performing our own tests on the material to get any.
Oh, absolutely.
Kill any missing data that I
Yeah, it would be great if you could want testing your own material properties. The material test lab's right there. But that's typically how you present that information. And then just want to echo Bryce's comment about factor safety requirement, what that actually is. Just having a reason why. Not that you did, but just to make it clear. Other than that, I just had small comments, like for the very beginning, when someone mentioned competitors, I think that's really important to know, because you just want to make it, you're trying to sell this to us, so make a compelling case for what sets your system apart. And then, what else did I have? Mostly just clarifying things, like you mentioned on, I think, your equations of motions, you mentioned you're gonna use these to make a control system. Not being a controls guy, it'd be nice to just see like a basic block diagram of, okay, well, this is the general layout, and we're at least thinking about this as opposed to saying, we'll think about this and we can use it for this, and we need to do this later, but for now, here's our equations. So we can see everything